I feel kind of comfortable not spending a whole lot of time on the heat and power, because, well, we spent a lot of time already. Let's just look at the example problem, though. Cut right to it. And you know, one thing that we've added to the Energy Tech program over the past few years is putting in a lot of stuff like this in 101. And I'm looking right away at this and seeing that it's a lot of mass balance and energy balance and just kind of keeping track of units. Oh, and Patrick Brown is going to try to talk about why our coal is so cheap next week. What I'm still not going to quite figure out is why there's zero fluctuation, why it's just flatline. It seems like it would be much more volatile.
Should we ask him?
Yeah, definitely ask him. He thought he kind of was trying to explain it to me, and I asked him to be prepared for it. So yeah. Because I just see sulfur here, and he's like, "Oh, it's high sulfur." I'm like, it didn't seem like it was all that high sulfur to me.
You guys just got some too, didn't you?
We're going to order some coal, yeah, from Cloud Peak, and burn it down the Bitterroot and see if we can't clean it up.
That's awesome.
Yeah.
It's going to be neat to see that happen.
Yeah. Okay, so page 157, problem 6.1. Okay. Manager of a power plant, co-fire switchgrass with coal, there we go, as a means of reducing sulfur emissions from the plant. However, the plant engineer warns that alkali in the switchgrass can lead to ash fouling in the boiler. The raw coal, which contains virtually no alkali, has a heating value of 28 megajoules per kilogram. That's right there. And a sulfur content of 4%. There we go. What is the maximum weight percent of switchgrass that can be blended with the coal without producing ash fouling?
It's a maximum proportion.
Let's see how far he gets with the solution here. What's the fouling threshold? Okay, so the switchgrass is 10% by weight. No alkali. Okay, there's your zero alkali. Okay, so he's going to say 100 kilograms of mixed fuel. So X is going to be the weight of the coal. Y is the weight fraction of the switchgrass. We'll form an energy balance for the fuel mixture. Okay. X kilograms, Y kilograms equals X megajoules of mixed fuel. Since the problem asking, let's do an alkali balance. The limit of fuel alkali content to less than 0.17 kilograms per kilo, or well, 0.17 to 0.34 kilograms per kilojoule. Let's select the lower limit of 0.17. Let's put everything together. Sorry, I'm going kind of fast. This is some kind of previewing, and then we can slow down. Sulfur 28%, part B. You guys want to just kind of go through that slow, step by step? Yeah, let's do that. I'll get my pad going here. Yeah. So basically, what we're trying to figure out, since we know that the ash has 10% or the switchgrass has 10% ash content, what weight fractions can we pump in to not foul with the alkali? So let's see if I can't get both of these on the same. Hello? I have this problem lately. I don't know why. Come on, Microsoft. It's the ghosted. There we go. Okay, so basically we've got coal is here, and we're going to call that X. And we've got the switchgrass is Y. And then when we're done, we're going to end up with some chunk of fuel, right? And the question is, where's this dotted line? Switchgrass, and there's the coal. Okay, and that's X plus Y, and this whole thing is 1. And I think he says he wants to use So since coal is 28 and switchgrass is 18, what we're looking at is energy total equals X times 28 plus Y times 18. So an X plus Y has to equal 1. So whatever I give to X, I take from Y. So if Y equaled 1, I would just have 18. If X equaled 1, I'd have 28. That's my range of energy. And this is in megajoules per kilogram. Megajoules per kilogram. Okay, and now we're looking at alkali. So let's just say alkali total equals so the alkali is actually 15% of the ash. So that's why we're multiplying the 10%, the 10.1 times the 15.1. So, and it's basically, X times 0 times 0, because there's no ash, plus Y times 10.1 times 15.1. Boom. Okay. Fine. Equals A. So we're kind of looking for A, and we're also looking for X. We're looking for Y. So right now we've got 2 equations and 3 unknowns. Well, maybe 4 unknowns if you count energy total. Okay, and the fouling we're looking at. We got to be less. So A has to be less than 0.17 kilograms per gigajoule. Fine. So let's see this one. This one's a little more complicated. I'm going to write it out as, we'll just call this, this guy's equation 1 up here. This is equation 2. This is equation 3. So what we're looking at is equation 2, which is y times your 10.1 times your 15.1 divided by x times your 28 megajoules per kilogram plus y times 18 megajoules per kilogram, keep the units in there, times, now here's kind of the little tricky part with the units, megajoules per gigajoules. So we've got to get to that 0.17 kilograms. So the kilograms right here are going to end up in the numerator. These guys are all percentages, so there's no units in the denominator. Times 1,000 megajoules per gigajoule. And you've heard me talk about when you're solving a problem, you're always solving 3 at once. This little guy right here, there's your number, the mega and the giga are your powers of 10, and then the joules obviously are the units, equals 0.17 per gigajoule. And really, guys, from here on out, I mean, we can just call this one equation. There's basically x plus y equals c, or mx plus y. The other equation, I didn't label it. It's basically equation 0. It's just x plus y equals 1. So, all right. And I have a phone call at noon. And so almost all these problems are just looking at the units. That's why you got to pay attention to them. Make sure you write them out, and good.
Write them out, cancel them out.
There you go. Okay.
Thanks, Patrick.
Yeah, and Patrick will be here in a week. I think we got you set up for the tour on Monday.
Perfect.
It's going to rock. Yep.